And this morning we continue where we left off yesterday with Thomas, and he will tell us more about XOR games and I guess games in general.
Maybe XOR games actually. So I think yesterday I was a bit too ambitious, so we'll just cross this out and stay with XOR games. But at least we can finish this morning what I had planned to say about two-player XOR games yesterday, and I think this will be good enough for this tutorial. So I want to remind everyone of the formalism that I had introduced yesterday and what we showed, also in case anyone in the audience was not here yesterday. So I defined what these two-player XOR games are. Right, so such a game is specified by two things. One is a probability distribution, the other is a function, which is the sort of success criterion in the game. And the game is played like this, so there's two players and there's a referee. The referee first chooses a pair of questions, S and T, according to this distribution. So distribution is over two question sets. Questions I'm just labeling using integers from 1 to n. So question S goes to Alice, question T goes to Bob. Each of the players sees their own question, they reply an answer. These answers are just single bits. And then the referee checks that the parity of the answers that he received is equal to this function of the questions. So that's just this bit. So it's a public function. The players know everything in the game. The only thing is that they only see their own question, and they try to succeed. So they try to achieve, match this criterion of the highest possible probability. And for this, we allowed them to use quantum mechanics. So they can have an untangled state psi, and when they receive their questions, Alice applies a binary projective measurement, AS, and Bob a binary projective measurement, BT. So there was one quantity that we are looking at, which is the bias of the game, so that I know to be the star. And this was the maximum probability of winning minus probability of losing. So it's a quantity that's between 0 and 1. So just using quantum mechanics, we rewrote it as in this way, as the supremum over all possible strategies. So what's a strategy? It's a dimension D, then it's an entangled state psi in CD tensor CD, and then it's choices of observables, AS and BT. So these are Hermitian matrices which square to identity. Right? It's Alice's measurement. AS is the projector on 0 minus the projector on 1. And this is the projector on 0 minus the projector on 1 on question T for Bob. And so the bias we saw could be rewritten as an expression like this. So sum over all possible questions, probability of the question, minus 1 to the expected answer, times this here, which is the probability that the players give answers that have parity 0 minus the probability that they give answers that have parity 1. Just expanding this as AS0 minus AS1 and BT0 minus BT1. And one important theorem that we saw is that this optimization problem here, which is a priori unbounded optimization problem, we could rewrite in a simpler form as an optimization problem over real vectors. I kind of mess up the real part, but let's just take it from here today. So you can take these vectors to be real 2n dimensional vectors, and then you're just optimizing the same function here, where I just use GST to represent this, because it's just simpler. So this is an n by n matrix G, and then the dot product of the vectors xs and yt. So this was this equality there was due to Thilson, and in proving it, we showed the following. So this is what we saw yesterday. For every two-player XOR game G that has questions between 1 and n. So we saw two things actually. So we saw that first of all, there exists an optimal strategy of dimension at most, so D, this D parameter at most D 2 to the root n. Actually, I only showed you 2 to the n, and then I said, well, if you're a little bit careful, you can prove this bound. So this was due to Thilson. And then we also showed that for every epsilon positive, there is an epsilon optimal strategy that has D less than 2 to the, and I think if you're careful, you can get constants like this. Where epsilon optimal, it means that the success or the bias that you achieve is at least the optimal bias 1 minus epsilon, right? And this was due to Regev. That's what we saw. So today I want to prove lower bounds. So go look at things in the other direction. So this is what we're going to see. for every n, there exists a two-player XOR game G that has question sets of size, actually G with questions in. So this game will have n squared questions per player, such that any optimal strategy requires D at least 2 to the n. So we're kind of 2 to the n or 2 to the 2n. I think 2 to the n. So we're pretty close. I shouldn't be that close. So let's see. Maybe it'll be the 2 to the 2n. I'm not sure. So a little factor missing, but we'll get pretty close. So this is what I want to show. That's what we'll spend our time on today, and it'll be based on exploring this equality a little bit more, writing this as a semi-definite program, using the dual semi-definite program, and looking at this dual as putting constraints on the structure of strategies that can be optimal in an XOR game. So we'll have general structural results, and then afterwards I'll give you an example. I mean, I'll give you this game. It's explicit, very simple game, and we'll show that the dimension needs to be large. The thing that I won't get into is trying to match the second bound here. And I think the best result that's known here is that for every epsilon, there exists a game. Actually, I don't know how many questions. So this is a game such that epsilon optimal strategies require dimension at least 1 over root epsilon. And this is a result by Harry, Borman, Briette, Borman, and Toner from 2009, I think. I don't know how many questions. Do you know? I think it has a lot of questions. Right.
A lot of questions.
So the game is going to involve a lot of questions. I don't know how many. I guess some dependence on epsilon. So there's a gap here. I think this is the best lower bound that's known. So I don't think we know which of these is true. So the thing is that this result here proves the lower bound on the dimension of the vectors. And the vectors need to have at least that dimension. If you could argue that when the vectors have this dimension, the strategy needs to be obtained through Tillotsen's construction, so there's an exponential blow up in the dimension, then you'd get 2 to the 1 over root epsilon, and there wouldn't be such a big gap. But you can't argue this. It's not because the vectors have dimension 1 over root epsilon that the strategies need to have dimension 2 to the 1 over root epsilon. There's an interesting gap here that maybe it's interesting to try to close. But I won't get into that. All right. That was the summary. Questions? Everyone's ready?
Let me ask you something.
Yep.
The first two claims,
Uh-huh.
one on the top and one on the bottom,
Okay.
don't seem to be quite consistent.
They're not consistent? Okay.
Well,
n over 2, right? I messed up the... Is it better if I write this? So we'll correct this when we actually prove it. We'll see. Yeah. All right, so I'm going to... Can everyone see this board here? Yep. And this board also? I want to write something that will stay. So. Okay, so I'm going to give you an equivalent expression for the bias that's based on the inner products here. So for a two-player XOR game, we can write this bias as like this. So maximize trace of mx. So M is going to be this matrix. It's a block matrix that involves, right? So it's a 2n by 2n matrix, right? G is this game matrix that I introduced over there. There was n by n, and now I just put a G there, G transpose, and then zeros and zeros. So X is also a real 2n by 2n matrix, which is positive semi-definite. That's positive semi-definite, right? Not and X I equals 1. So the diagonal entries are 1. So that is supposed to be just exactly a rewriting of the maximization over inner products of real vectors over there. I don't know if everyone is familiar with positive matrices and their relationship with inner products. So if you take a positive matrix like this, it's the same as saying that this matrix can be written as the matrix of inner products of vectors. So to see the relation between this here and that over there, you take x, x to be the matrix which has as inner products the inner products of the vectors xs and yt. So you write it like this by blocks. Here you'll have inner product between the xs and xs prime, xs yt, yt, xs prime, yt, yt prime, right? It's basically, it's equal to, you could put the vectors x in rows here and y's in rows, and then take the product of this with its transpose. So the vectors x like this, and yt prime like this, and you do the product, right? So if you take any family of real vectors and you look at this inner product matrix, it's going to be positive, and conversely, for any positive matrix, you can write it as a matrix of inner products of real vectors, xs and yt like this. So the constraint on the diagonal coefficients being equal to 1, what's on the diagonal here, it's just the squared norms of the x vectors and then the squared norms of the y vectors. So this constraint is the same. Did I write the constraint? I didn't write the constraint. There's a constraint over there that says that the vectors should have unit norm. Positivity is just to make it an inner product matrix, and that's it. And then when you look at this expression here, you see that the G matrix acts on xs, yt, and then because they're flipped yt, xs, so this is why there's a transpose here, and this is why there's a half. But the objective function here is exactly the same as the objective function over there. Okay. Why did I write it like this? Because this is exactly semi-definite program. So maybe not everyone has seen a semi-definite program before. It's something like this. So it's an optimization problem. It's the optimization of a linear function. So that's the linear function. The variables are x. And this optimization is performed over the set of positive semi-definite matrices under a certain number of linear constraints. And these are my linear constraints. That's a convex optimization problem. It has the advantage that because of the particular structure that you're optimizing over the cone of positive semi-definite matrices, it's very efficiently solvable, even in practice, reasonably efficiently solvable, time polynomial in the dimension n here. The other advantage that we have of writing this explicitly as semi-definite program is that we can use duality. So this is also equal, I'm going to write the dual SDP now, to the minimum of sum over S of CS plus sum over T of dt. These are variables, they're real variables, such that the matrix half, and so again by blocks, in the upper left block I put a diagonal matrix with the coefficients CS, and here a diagonal matrix with the coefficients dt, and this, so that's just a diagonal matrix, should be larger than the matrix M. That's another semi-definite program, right? I'm optimizing a linear function over some positive semi-definite, so this is larger than positive semi-definite constraint, or positive semi-definite constraint. And the two of them are equal by duality. So I'm not deriving, why this is the dual of this. I just ask you to believe me for here, but it's just, standard semi-definite duality. So we have a new expression for our bias. We're going to use that expression in order to put constraints on what are optimal vectors in the optimization, and then what are optimal strategies. All right. So just as a corollary of this new expression, we have the following. So we have that for every game, there exists some coefficients. So CS, dt, these are real coefficients. Actually, they're non-negative, such that any optimal solution xs yt, so to the optimization there satisfies that the norm of the sum over t of g s t x s is equal to CS, yeah, and the norm of sum over T of G ST sum over S, what did I do? Sorry. YT. So this is a vector, right? And this is a vector here again, equals DT. Okay. Why do we care about this? This might look a little bit obscure for now, but let's just prove it. And then the next thing that we'll show is there exists these relations on the vectors, they'll impose constraints on the strategies, on the AS and BT. And this is good because we'll start getting a handle on what do optimal strategies look like. And then we'll get to, we'll be able to move to proving lower bounds on their dimension. But for now, we're just moving at the level of the vectors. So this is just something that has really nothing to do with the game or quantum mechanics. It's just understanding what this dual formulation over there is teaching us. Okay, proof. Well, let's take optimal. So let's take optimal solution to the primal here, or actually to this optimization problem. Actually, let's rewrite this optimization in a slightly different form. So this maximum over XS and YT I can rewrite like this. I can move the summation over, let's say, S a little bit inside. So I can write it as maximum, then I'll have T outside, and then I'll put sum over S of GST XS. Right? It's just exactly the same thing. But if you write it in this way, you see that if the vectors XS are fixed, then the optimal choice for YT is clear, right? You want YT to be parallel to this vector, and it should be normalized. So the best choice of YT is this divided by its norm. And so this will exactly be equal sum over T of the norm of sum over S of GST XS over XS and norm of XS equals 1. All right. So we know, given the X, what is the best choice of Y. Now, okay, maybe I'll continue over there. Let's use the formulation over there. So let's take X to be this matrix, the matrix I had defined before, right? XS dot YT, and let's take some coefficients CS dt, which are an optimal solution to the dual. Maybe I can call the dual double star. The primal will be star. The dual will be double star. Okay, so we take this optimal solution. So what do we know? We know that the, let's write trace of the difference of the two, my constraints there that I have over there. So a half is matrix diagonal D. I take this minus M. So that's a positive matrix. And then I multiply it by X. We claim that this is 0. So why is it 0?
What does X do?
X is the matrix that, so I took an optimal vector solution and then I wrote the inner product matrix X. So X is an optimal solution to the primal problem. So why is it 0? Because if I expand it, I get two terms. Okay, and so the first term will be this matrix times X and the trace of that. So the trace of that is just the sum of the diagonal coefficients of X multiplied by these. Diagonal coefficients of X, they're just the norms of my vectors. They're just 1, all of them. So the first term will just be a half sum over S of CS plus a half sum over T of DT. And there should be a half here, I think, probably. Right? I get this minus trace of mx. But these, and here I'm using duality, right? I'm using that the optimum of the two formulations of the problem are equal. This is the optimal of the primal, this is the optimal of the dual, so I get 0. Okay, fine. So this expression is 0. What is it? The trace of the, the trace of the product is 0. Now X is a positive semi-definite matrix, and this matrix here is also positive semi-definite. So the product is not, but I guess I could rewrite this. Okay, let me rewrite it, sorry. Trace, using that X is positive, I can put, all right. I want to say that the product is 0. This is true, but Alright, sorry, I'm going to skip this step because I'm not too sure how you do this again, but basically using the fact that this matrix here is positive, this matrix is positive, the fact that the trace of the product is 0 implies that the product itself is 0. Maybe someone can tell me why?
If you write in the eigenbasis, you can see it, but
okay, alright. So we have that the product is 0. And let's look at the diagonal coefficients of this product here. So I look at this and I look at the diagonal coefficients. So for example, the SS coefficient, so the upper left block, the SS coefficient is what? So I get half CS times the 1 here, minus, so this M has this G on the, so upper left corner there's nothing, there's G on the upper right corner, so I'll get minus sum over T of GST XS dot YT. That's the SS coefficient of my product here. And then the observation that we made before is that this sum here over, where is it? Sum over, well, I did it for the sum over S. Okay, fine. So the TT coefficient is DT minus sum over S of GST XS dot YT. Okay. And this sum over S of GST XS dot YT we saw is equal to this norm here. So this is equal to a half of DT minus the norm of the sum over S of GST XS, where I'm again using that the XS and YT are an optimal solution. Okay, so dividing by 2, we get the claim. So this means that if I take a XOR game, two-player XOR game G, I solve the dual semi-definite program here. I get these real coefficients CS and DT, and what these real coefficients are telling me is simply what is the norm. If I take an optimal vector solution, XS and YT, what is the norm of these sort of marginals here? This is kind of, well, it's just saying what are the norms there. This is not too surprising. I mean, I just did a calculation and fine, there's these relationships that hold, right? All right. Okay, now for something more interesting. We're going to go to the strategy and say something about the strategies. Is there questions on that? All right. So again, I fix the game and I fix psi AS BT, an optimal strategy, so that achieves the bias in G such that the strategy is non-degenerate, so in the sense that such that if I look at the reduced density of the entangled state on Alice, so I trace out Bob, and then I can also look at the reduced density on Bob, trace out Alice, side by side, so that these two are invertible. This is just an assumption I'm making. If they're not invertible, it means that there's just some, part of your Hilbert space that you're not using because the entangled state has no support on it, and there's no point in having such a thing. You could just cut it out, right? So we can always assume this holds. Okay, then a number of things hold. First is that we have an analog of these these relations that apply directly to the observables in a strong sense. So we have that the sum over S of GST AS squared, so remember these are Hermitian matrices, is equal to over 2 times the identity. Also we'll get that the sum over T of GST DT squared will be equal to CS over 2 identity, and we'll also get that every AS, so each of these observables commutes with OA, and the BT, they commute with the reduced density on Bob. So this is very strong. It's almost surprisingly strong because you're making statements really directly about some relations that the observables should satisfy and how these observables should relate to the state, which are not things that are directly observed in the game, right? The game, winning in the game, this really involves only probabilities that are the result of applying the observables on the state. And here you're saying something about the observables themselves. This commutation relation also, it's kind of surprising. I mean, the different observables, of course, in between themselves, they don't commute. Otherwise, you would have something that's like a classical strategy. But this is saying that the state and the observables have to be compatible in this kind of strong sense. So from this, I'm going to prove this. And then we'll use it, we'll apply it. I'll apply it to show you what it's saying about the CHSH game. This will actually already be interesting. It'll tell us something about how rigid this CHSH game is. And then we'll apply it to another game. And just from the fact that these relations hold, but on a specific example, the relations will look much simpler, we'll deduce that the dimension of the observables must be very large, because any observables that satisfy the relations that we'll get will need to have a very large dimension. That's where we're going, but first let's do this. It'll come as a corollary of, I have too many corollaries, okay. This is a corollary of the corollary. Then we'll have corollaries when we do the applications. Maybe I should write it, so it's corollary 2 and the other one is corollary 1. The proof is not hard. It uses one nice observation that I'm going to write first as a separate claim. So suppose that you have two matrices A and B that are such that when you apply A to left hand side of a state psi, you get the same thing as applying B to the right hand side. Then A must commute with the reduced density and B must commute with the reduced density. And we'll actually get a little bit more than that. So we do the proof of this, because it's a nice rewriting trick. I think a nice way to nice trick to work with this arbitrary entangled state psi. So let's write psi in a Schmidt basis. Sum over I of some coefficients lambda I ui vi, and let's introduce an operator k. So I'll just define k. which is just sum over I of lambda I ui, let's have it vi ui. The point of writing this in this way is that then I can write psi as simply identity tensored k applied to the state sum over I of ui right? But this is maximally entangled state. So that's going to be useful for us. So now let's take our assumption up there and let's write A tensored identity psi. This is equal to, so psi I can write in this form, but A tensor identity and I tensor k commute because they act on different systems. So I can write identity tensored k times A tensored identity applied to the state sum over I of ui. Since this is the maximally entangled state, when I apply an operator on the left hand side, it's the same as applying the conjugate on the right hand side. So I'll get, or actually it should be a transpose, right? So I'll get identity tensor A transpose times the same thing. Now when I look at identity tensored B applied on psi, well, this is simply identity tensored bk applied to sum over I of ui. And then again using the fact that the state is the maximally entangled state, so here I have an operator bk that acts on the right hand side of the state, and here I have another operator k A transpose that acts on the right hand side, and the two vectors by assumption are equal. This implies that k A transpose equals, oh sorry, so A and B should be Hermitian here. Hermitian. Alright. So I get this. This I just use the fact that this is maximally entangled state. Alright. Let's multiply by k dagger on the right hand side. So I'll get that k A transpose k dagger equals to B k dagger. This is a Hermitian matrix. If I take the conjugate transpose, because A is Hermitian, it doesn't change. This here, you can check, you can do the calculation. This k dagger is just sum over I of lambda I squared vi. It's the reduced density of psi on ball. So I have this Hermitian matrix which is equal to B times Ho. I can take the conjugate transpose, this doesn't change, this becomes Ho times B dagger, B is Hermitian, so I have that B Ho equals Ho. Right? This one is Hermitian, this one should be as well.
You said that
I
again?
lost everyone. Yeah.
No, just the last. So
How about here? This was okay, or we accept this, or using my little tricks?
Okay.
Okay, so we multiplied by k dagger. Is this okay? So, well, I just rewrote this, that the fact that this is the reduced density, you can just check. Okay. Now I can take the conjugate transpose of my equation. What happens to the left hand side? Nothing. I mean, I get k, I get A transpose conjugate transpose, but I'm assuming that A is Hermitian, so I just keep the same thing. I get exactly the same thing, but on the other side, well, I get Ho dagger, but this is just Ho and it's Hermitian, times B dagger, which is like this. So I get this. Here, to obtain this last line from the line before, I just took conjugate transpose. Left hand sides didn't change, and right hand side. So I get this commutation relation between B and Ho. And I got it also. Right. So that's the end of the claim. Let's prove corollary. It's going to be pretty easy once we have the claim and corollary number 1. So let's take, well, we already have it, right? So let's take this optimal strategy. Because it's an optimal strategy, if I look at the vectors that are derived from that strategy, like when we did in the proof of the equality that's all the way on the left there yesterday, So if I define these vectors, AS tensored identity applied to psi, and I define a vector YT, which is identity tensored BT applied to psi. And let's cheat a little bit. Let's assume these vectors are real, right? Or make them real in using some trick. Because it's an optimal strategy, they are an optimal solution to my problem over there. So I can apply the corollary. And the corollary will say that, well, actually, remember in the proof of the corollary, we had argued about how these vectors YT should relate to the sum over there. Right? So from the corollary number one, I know that the vector YT, which is identity tensored BT psi, should be equal to the sum over S of GST x XS, which is AS. And I'll put it like this, tensored identity psi. Right? This is an observation that we had made before. It just follows from the same. I mean, now I'm just talking about equalities of vectors, right? So this is exactly what we had done before when we were saying the vector XS should be equal to the sum over S of GST times the vector YT. Sorry, the vector YT should be equal to the sum over S of GST times the vector XS, and we get this. Now I can apply the claim. The B in the claim is just going to be BT, and the A in the claim is just this big matrix here, which is a Hermitian matrix. So from the claim, I already get half of my corollary, which is that BT commutes with rho B, right? Just using this. And then by symmetry, I'll also get the same thing for the A. So AS also commutes with rho A. All right, good. Now we only need to derive the thing about the squares. Let's see how we get it. I'll use the same trick as I used in the claim in writing this psi as identity tensored K. So exactly what we were doing here with my A and B, which are this B and this A. And we had derived this equation, right? K A transpose equals BK. So let's just write, so claim this implies this. The first thing it implies 1. And then the second thing I can use it for, just using the formalism, is to say that, okay, so K A transpose, so I'll get K A transpose, where I'm using A to denote this thing here, A, is equal to BT times K. Right? I'm just doing exactly the same thing as before, but now I have specific matrices in mind. Okay, let's square this equation. So multiply left and right hand side by the daggers. So I'll get that K A transpose dagger K dagger is equal to BT K dagger. Oh, I'm doing it the well, no, BT dagger. Alright? Just multiply. I took the dagger of this thing and then multiplied the left hand side and the right hand side. Now BT, this is rho B. And I just proved that BT commutes with rho B, so I can commute it, and then I get B times B dagger. B is an observable, this is just identity. It simplifies. So here I just get rho B, or KK dagger. And I did everything the wrong way around, but oh, sorry. All right. This was not quite correct. What we had gotten is that when I did the calculation up there, is not that YT, this vector, is equal to this vector, but it's equal to this vector divided by its norm, right? Where the norm is the coefficient dt over 2. So actually there should be a dt over 2 coefficient here. Sorry about that. So there should be a dt over 2 also here and here. Over 2, dt over 2.
For the top line, it's 2 over dt.
This should be 2 over dt?
Or it's put on the left side.
Oh yeah, yeah. But this is, but here it's correct. Okay, Yep, thanks. All right. Now, by my assumption that we had somewhere on the strategy being non-degenerate, so this invertibility assumption, K is invertible. Basically, I'm just using that all the, these span the whole space and the lambdas are non-zeros. So I can invert K. And so we get that A.
Should it be a square, the dt over 2 also, when you apply the equality and...
Yes. Thank you. So I'll get that A transpose dagger is equal to dt squared over 4 identity. And this is what we wanted up to me forgetting the squares up there. Because remember what A was? It was this matrix here. I can take the transpose, right? This is symmetric, so I can take the transpose out. Actually, the matrix A is Hermitian, so this is just A squared. And A squared is this matrix here. So I have what I had up there in the corollary. Exactly this, that's my A squared, and then I should have not have forgotten to square these. Right. Corollary proven. So we didn't use much, right? We use the fact that the vectors, we use corollary 1, which is saying that optimal vectors must satisfy particular constraints on how they are aligned with each other, right? The yt should be parallel to the sum over s of gst xs. And then we use the information that we got from the dual SDT. And we were able to translate all these constraints into constraints that apply directly to optimal strategies. The only assumption we used is that the strategy is optimal and that it's non-degenerate in the sense that the entangled state has support on the whole space, both on Alice's side and on Bob's side. So now let's do corollary number 3, application, and see why this is, why these constraints, how do they look like in a particular example and why they're useful. So, by the way, I guess yesterday I had promised I would say something about C-star algebra, or I'd rather not say it because I'm going to say something that's probably wrong. But what this is saying is that any optimal strategy must correspond to a representation of the universal C-star algebra, which is generated by observables that satisfy these relations. And so the question of proving lower bounds on the dimension of optimal strategies, this is just the question of proving lower bounds on the dimension of irreducible representations of this universal C-star algebra, where these relations hold. And this is what we're going to do, except I'm not going to define what the C-star algebra is, or we're not going to see representations, but this is basically what we're just going to do. All right. First example, and it's a shame that the first example comes an hour and 45 minutes into the lecture, but let's look at the CHSH game. So probably all of you have seen CHSH at least as a Bell inequality. The game matrix that's associated to it is this matrix, so a quarter 1 1 1 minus 1. So it's a game where the questions there's just 2 questions to Alice, these 2 rows, 2 questions to Bob, the 2 columns, and if we label the questions to Alice using 0 and 1 and 0 and 1, then the constraint that they have to satisfy is that the answers A plus B is equal to the AND of the questions. So the parity of the answers should be 0. So this is remember this is minus 1 to the correct answer. So the parity should be 0 in all these 3 cases, except when the 2 questions are 1, then the parity should be 1. So, and one thing that we know is that the bias for this game is root 2 over 2. This is how well you can do. Actually, we're going to rederive it. So let's apply our corollary to this game and see what it says. So for this, we have to compute these coefficients, CS and DT. There's going to be 4 of them. In order to compute them, let's just go through what we had written up there and try to solve directly this optimization problem that corresponds to the bias of the CHSH game. So the bias of the game I can rewrite as a quarter. This is just the coefficient here. I mean, I sum over all S and T of the coefficient a quarter times the inner products of the vectors, right? So I'll get U0 dot, x0, y0 plus x0, let's say x1, y0 plus x0, x0, y1 minus x1, y1, right? Maximum over unit vectors of all this. And then I get a quarter, and we can rewrite this as x0 plus x1 dot y0 plus x0 minus x1 dot y1. And if we make the optimal choice of y0 and y1, what we'll get is a quarter times the norm of x0 plus x1 plus the norm of x0 minus x1. Okay. So what's the optimal choice here? Well, clearly x0 and x1 should be orthogonal vectors. This is what's going to maximize this expression here. So x0 orthogonal to x1. And in that case, we'll get that the bias is a quarter times, and this will be root 2 and this will be root 2, so I get 2 root 2. So we get root 2 over 2, right? So we proved this already, that the bias was root 2 over 2, just using the manipulations directly at the level of the vectors. While doing this, we also got, by the corollary up there, this is saying that these biases CS and DT should be these norms there. So we also get that C0, C1, D0, D1, these are all the same, and they're equal to twice the norm, and this was the norm, so they should be equal to 2 root 2. Right? This that looked very complicated before, this sum over T of GST, or rather sum over S of GST XS, this is just this, right, in this case. X0 plus X1, that's for T equals 0, and X0 minus 1, minus X1 for T equals 1. So we computed for the CHSH game what these biases are, and now we can apply corollary number 2 and say what it says about optimal strategy in the game. And let's do this here, right? The proof we don't need. Okay, so by corollary 2, we get that the same relations that held at the level of vectors hold at the level of the observables. So I get that A0 plus A1 squared should be equal to my bias squared. So this is going to be 8 divided by 4. So twice identity. And I also get that A0 minus A1 squared should be equal to the same thing, twice identity. And I'll get similar relations for the B observables. Now, because these are observables, you can expand the square. A0 squared is identity, A1 squared is identity. This 2 identity goes away. And we'll get that, basically both of them imply the same thing, which is that A0, A1 plus A1, A0 equals 0, and we get the same thing from the B's. B1 plus B1, B0 equals 0. So the observables that the players use when they play optimally in this CHSH game must anti-commute. Also, they must commute with the reduced density of the entangled state. From there, you can do one more step or 2 more steps that I'm not going to do, but they're very simple. You can deduce that, basically this pair of observables that commute, what are the typical observables that commute X and Z Pauli matrices, right? Well, you can deduce that up to isometry, this is what they must look like. So you'll get that A0 must have the form of X tensored identity up to an isometry, right? In particular, dimension of this is even. So this is Pauli X, dimension 2. So this doesn't necessarily have to have even dimension, but up to some isometry, I'll get this. A1 should be roughly of the form, sorry, this is not roughly, it's exactly up to isometry. And then the B's will look like this. The B0 will be A0 plus A1 divided by root 2 tensored identity, and B1 will be X minus Z divided by root 2 tensored identity. And now my reduced density matrix, let's say on Alice's side, well, it must commute with X tensor identity, it must commute also with Z tensor identity. And this is saying that necessarily it'll be written as, for this first qubit that I singled out, it'll just look like the totally mixed state. And then some kind of remainder that I'm not saying anything about. So let's say sigma A. And also on Bob, I'll have the same thing. So identity over 2 tensored sigma B. So these really follow just from this, and the fact that the reduced density should commute with Alice's observables and Bob's observables up to some manipulation that I'm not doing. But what it shows is that essentially optimal strategies in that CHSH game are unique. They must look like X and Z Paulis for Alice, and the slightly shifted bases for Bob. And then the fact that reduced density here is identity over 2, well, you don't have many choices for the entangled state that gives rise to these reduced densities. It's only an EPR pair in between Alice and Bob, tensored with some junk that anyways they're not touching.
I have a question.
Yeah.
So before you filled in the Pauli matrices in the relation upstairs, you have never those. You don't have A and B coupled.
Yeah, that's true.
How do you get the relation between the A's and the B's?
Yeah, you're right. So is that's not written anywhere, right? So yeah, you get it, but you're right that it's not going to follow just from this. You get it from what we had before, right? When we were
Should that be like identity tensor X plus Z over root 2?
This one here?
Yeah.
No. Where? You want to put the identity here?
They shouldn't commute with A's and B's don't commute.
Oh, yeah. Sorry. No, I mean, this is the whole of Alice's space. So this is like 2 dimensions. This is huge, whatever dimension, and this is the whole of Bob's space. So then I'm going to take A0 tensored B0, right? The way you get these relations is that because is what you had from you actually have more when these relations on vectors. You'll have things like, for example, identity tensored B0 psi. This is my vector Y0 should be equal to A0 plus A1 by root 2 tensored identity psi. And this is my sum of GST XS times the coefficient dt. And so from this, which holds at the vectors, I mean, we observed it up there, right? What is Y0 as a function? Y0 is X0 plus X1 divided by its norm. This is just rewriting that. But then using the manipulations that we were doing before with this K operator, you can deduce that that B0 should be of this one.
Thank you.
You have it. Yeah, I think I erased it already.
Thomas,
Yeah.
another question. You could have some more complicated tangled state between A and B, which gives these reductions, right? Why you can say you just have an EPR pair between these 2 qubits and the rest is?
I have an EPR pair here, right, on the register on which I applied this isometry, which makes A0 look like X and A1 look like Z. I'm not saying how the entangled state looks like here.
Well, you only know that the reductions are given by row A and row B, right? And you could have any entangled state that gives rise to these reductions, right?
No, I also know from the corollary that these reduced densities should commute with the observables. And if you have to compute with both x and z,
Yeah.
you have to be equipped multiple of the identity.
No, I agree that row A and row B should be.
Ah,
like
so
this.
sorry, what's the question?
But the question now, you can have some other entangled states with that reductions. No?
I mean, like what? I mean, well, this gives you the squares of the Schmidt coefficients, right? So up to phase.
Well, we have this other part of the.
The other part I don't know what it is. Yeah.
Yeah.
But it has to be a tensor product because it has to commute with all those operators. Like if you have a
Oh,
No, it can be even if it's a problem, but then you can have some entangled state that once you trace out, you have this structure. What I don't see is that the only compatible pure state psi,
oh, it's not
A and B
necessarily a
is-
tensor product. You're saying?
Yeah, right.
Really?
No, I don't know, but I don't.
Okay.
Yes.
Yeah, I kind of assumed that this implied that my entangled state must have the form that I could tensor it like this, where this would be an EPR pair and this would be some junk, right?
But suppose the junk is also an EPR pair,
Yeah.
and the A and the B's act on different halves of EPR. Like Alice acts on an EPR pair entangled with Bob's junk, and Bob acts on an EPR pair entangled with Alice's junk.
Oh.
Like you have to rule that out somehow.
Yeah, you're right. You're right. Okay. Well, you can do it. I have 2 minutes. I want to give you this dimension lower bound. So, anyways, I already glossed over some stuff when I was doing this. So, this you can find in a paper by Matthew McCaig and a couple co-authors from 2 or 3 years ago, where they also do the approximate case. So you can show that if you're not optimally playing the CHSH game, you're achieving this bias minus epsilon, then all these relations hold up to some epsilon or square root epsilon. Well, now what were equalities before are going to hold, with distance epsilon as measured by the Frobenius one. Okay, so we have 2 minutes to conclude the dimension. So let me tell you what is this game, for which you can prove a lower bound of the dimension. It's actually a very simple game. We can do it generally. So what you can do is you can take a graph H, vertices, edges, a graph. So it looks something like this. Triangle maybe. And you can define a game from that graph. So G equals G of H. I'm not going to write it formally, but I'll tell you how the game is played. So the referee picks an edge at random, edge E at random, and this edge has 2 vertices, U and V. So for example, we picked this edge, and these are the 2 vertices, U and V, and he sends U or V, so one of the endpoints, to Alice. So with probability half each. And then he sends either the edge and a 0 or the edge and a 1 to Bob. Also with probability half each. What's the condition? Basically, we're playing a version of the CHSH game that's attached to this edge. So what Bob knows, he knows which CHSH game he's playing in a certain way. It's the CHSH game that's associated with the edge E. And in that game, he's asked the question 0 or 1. Alice, she only gets one of the vertices. To these vertices, this vertex here means question 0, and this vertex here means question 1. Except she doesn't know, she got either U or V. She doesn't know if she's playing this CHSH game or this CHSH game. But this is what they're supposed to do. So the criterion is going to be that, if you interpret this as 0 and you interpret this as 1, then the priority of the answers should be the AND of these bits here. That's the game. You're just playing CHSH games. Bob knows exactly which one is being played, and Alice knows only half of it. But actually, you can show it's, I'm not going to show it, but the bias of this game for any graph H is the same as CHSH. So if this is my graph, this is exactly CHSH, more complicated graph, it looks harder, right? Because Bob has full information about what he's doing, but Alice doesn't have full information. Still, you can succeed exactly as if I was just telling everyone, play this CHSH game or this CHSH game, or so as if Alice was also told on the edge. You get the same bias. And then, because I'm really out of time, I'll just write this and leave it as an exercise. If you take the complete graph on n vertices, then doing exactly the same calculation as we did for the CHSH game, you look at the bias for that complete graph, it looked like an expression, exactly the same expression, except that first we have to pick an edge at random. So we choose an edge at random, and then we get an expression like this. So using exactly the same calculation, you'll be able to deduce that Alice's observables in that game, in an optimal strategy for that game, should satisfy these anti-commutation relations pairwise. So you'll have that AU, AV, where this is the observable for questions U and V, plus AV, AU equals 0 for every U different from V. This is what the game is achieving at the level of the observables. It's showing that pairwise they anti-commute. If I didn't have the complete graph, I would have just a specific graph, then I would get pairwise anti-commutation relations for every edge in my graph. And then the question is, well, how large do you need these matrices to be? So I have n matrices which pairwise anti-commute. And so the last claim that I'm not going to prove, but it's actually a simple proof by induction, is that if you have n observables that pairwise anti-commute like this, you need dimension at least 2 to the n over 2 in order to realize them. Prove it by induction. It's easy for n equals 1, easy for n equals 2, and there's a simple trick which reduces the case of n observables to n minus 2 observables. I'm not showing you the trick, but if anyone wants to see it, I can show them. So as a consequence of that, we have that the dimension of the A observables needs to be at least 2 to the n over 2. Probably you can't write it, but we can see it. And this proves the theorem that I had announced at first. So here we have n possible questions to Alice, but there's 2n squared possible questions to Bob. So if we're sort of fair, we have to count, because I was assuming question sets to be the same, this is 2n squared questions per player. And then I get dimension 2 to the n over 2. So this is my, I guess this is sort of what I had claimed. I had claimed n squared questions per player. Well, this is what we have, right? N squared, because there's only n choose 2 edges, so n squared. So this is roughly what we have claimed. But I'm over time, so